Momentum in collisions 2. Often, parts of a chosen system exert forces on each other. However, because these forces are internal to the system, F net on the system as a whole is still 0. And we've mentioned that if the net force on the system is 0, that's when momentum is conserved. Let's try a problem here where we have a mass that runs into the wall. And in one case, it sticks. And in a second case, the mass bounces back. And what we want to do is we want to find the change in momentum. Momentum is a vector, which means whenever we have things colliding, it's very useful to define a coordinate system in terms of which direction is positive and which direction is negative. I'm going to go ahead and say that to the right is positive. That might come up as we move ahead here. Initially, the momentum of the ball is mass times velocity. So the mass is 1 kilogram, the velocity is 6 meters per second, positive. I'll accentuate that by putting a little plus sign there. 6 kilogram meters per second, positive. That's the unit for momentum. Mass has the unit kilograms, the velocity is in meters per second, so kilogram meters per second. At the end, the momentum of the ball is 0. It's stuck to the wall. So the change in momentum is final minus initial, negative 6 kilogram meters per second. That's how much the momentum of the ball has changed. Now, suppose that the ball bounces back at 3 meters per second. Well, initially, the momentum of the ball is still the same, positive 6 kilogram meters per second. But at the end, the momentum of the ball is mass times velocity, so that's 1 kilogram. And what's its velocity when it bounces back? When it bounces back, it's going to the left, which means it will have a velocity of negative 3 meters per second, which means, so in this case, how much has the momentum changed by? Final minus initial, negative 3 minus 6, negative 9 kilogram meters per second. There's a much greater change in momentum of an object when the object bounces compared to if it sticks to its target.